generating functions. So far, we have seen several ways of completely describing the distribution of a random variable. One is, in the case of a discrete random variable, specifying the probability function, or if it's continuous, the probability density function f of x. We can make this specification either with a formula, or a table of values, or a probability histogram, or in fact by naming the distribution. But in any case, this is a specification of the distribution of a random variable. The second is a fairly general procedure. I can specify the cumulative distribution function. This will completely determine the distribution in the continuous or in the discrete case. In this lecture, we want to add one third method, which uniquely describes a distribution and try and indicate what its advantages are in special circumstances. Now, this is motivated by the common use of Laplace transforms in mathematics and all of its applications, including engineering and statistics. This is a transform of the distribution. It's called the moment-generating function m of t of a random variable, or more precisely, the distribution of the random variable x. Definition of the moment-generating function. The moment-generating function, we'll shorten that to mgf, of a random variable x is a function of t, defined by m of t as the expected value of e to the xt. And of course, for this to make sense, we need this to be a finite value, at least in some interval of values of t. So the moment-generating function is a whole bunch of expectations, not a single one, because it's a function of t, the argument t. And you'll notice that if I put t equals 0, I get the expected value of e to the x times 0, which of course is 1. The expected value of 1 is 1. A moment-generating function evaluated at 0 is always 1. Here's a simple example. I've listed a probability function in the form of a table below, and I'm interested in obtaining its moment-generating function, the expected value of e to the xt. And we do this as usual by listing the values of e to the xt, multiplying each by their probability. So, for example, the probability 1/8 multiplies e to the 0t, and 3/8 multiplies e to the 1 times t, and so on, up to 1/8 times e to the 3t. So the moment-generating function is a polynomial in the quantity e to the t. Looks rather complicated. Let's suppose we differentiate it. We take one derivative, m primed of t. We get 1/8 times 0 e to the 0t, plus 3/8 times 1 times e to the t, and so on. Again, we get an expression, but this expression simplifies to something rather important when we set t equals 0, because then all of the quantities, e to the t, e to the 2t, e to the 3t, and so on, reduce to 1. In this case, we're left with m primed of 0, which, after I do some arithmetic, turns out to be 1.5. This is exactly the expected value of a random variable with this distribution. We've discovered something important. The moment-generating function can be used to find expected values. All we need to do is differentiate it once, and then set t equals 0. In fact, a moment-generating function can be used to find all moments of a random variable. This is the subject of the following theorem. Suppose a moment-generating function of x is given by m of t, the expected value of e to the xt. Then the expected value of x is m primed of 0, the first derivative evaluated at 0. E of x squared is the second derivative, m double primed of 0. And in general, for any non-negative integer k, the expected value of x to the power k is the kth derivative of m, again evaluated at t equals 0. We'll prove this in the simpler case of a discrete random variable with probability function f of x. We simply write down m of t, by definition the expected value of e to the xt, which is the sum of the values e to the xt times f of x over all values of x. If we take a first derivative, we obtain the sum over all x times e to the xt f of x. And then by replacing t by 0, we discover that e to the xt in every case becomes 1. We're left with the sum over all x times f of x, which is the definition of the expected value for a discrete random variable. When we take second derivatives, we get something similar. We get the sum of x squared times e to the xt f of x, and again replacing t by 0 leaves us with the sum of x squared times f of x. The sum of the values of x squared times the probability function, that's just the definition of e of x squared. So this result is the motivation for the name moment-generating function. In that sense, MGF will generate moments of a random variable. Moment-generating function for the Poisson distribution. proceed to calculate a few of the standard moment-generating functions, the Poisson being the first. I'd like to show that the moment-generating function takes the form e to the minus mu plus mu e to the t, but I also want to use the moment-generating function to find the expected value and the variance of a Poisson, something for which we already have a formula, in fact. And the first step, I think, is to write down the probability function for the Poisson. F of x equals mu to the x divided by x factorial e to the minus mu. This allows us to produce a moment-generating function, or at least a formula for one. M of t is equal to the expected value of e to the xt, which is the sum over x, e to the little xt, f of x. We need to evaluate that sum in this case. I'll replace f of x by its definition for Poisson, mu to the x over x factorial e to the minus mu. And since we're adding over x, and e to the minus mu does not change, it's a constant with respect to x, it makes sense to take it outside the summation sign. The other trick in evaluating this moment-generating function is to put together all powers of x, and there are two of them that appear here, mu to the x and e to the xt, which is e to the t raised to the power x. And when we put them together, we end up with e to the t times mu raised to the power x. The advantage now is that we see something of the form the sum over x, y to the x over x factorial, where y in this case is e to the t times mu. This you should recognize. It's the exponential series expansion. It's the series expansion for e to the y, or here, e to the t times mu. So we've established a form for m of t, e to the minus mu plus mu e to the t. Let's proceed to find the expected value and the variance. The expected value we get by taking a first derivative, m primed of t, e to the minus mu plus mu e to the t, that quantity times mu e to the t. And when we substitute t equals 0 in this expression, the values e to the t all become 1, and we're left, in fact, with the simple answer, e to the x equals mu. This is the expected value of a Poisson. Take the second derivative, use the same sort of algebra. Again, all expressions involving e to the t, when we replace t by 0, become 1, and we have m double primed of 0 is equal to mu squared plus mu, and that is the expected value of x squared. Remember the alternate formula for variance. The variance of x is e of the quantity x squared minus the mean ex squared. In this case, that becomes mu squared plus mu minus mu squared, or we're left with mu. For a Poisson random variable, we'll recall, both the expected value and the variance are mu, the parameter. Some properties of moment-generating functions. There are two results important for the application of moment-generating functions in probability. One is the uniqueness theorem. Basically, it says a moment-generating function uniquely determines a distribution. In other words, if I have two random variables, x and y, and they have identical values for the moment-generating function, then those two random variables have the same distribution. By the way, having the same distribution for x and y doesn't mean that x and y are identical. If you toss a coin 10 times, and you define x to be the number of heads, and y is the number of tails that appear, clearly x and y are not identical random variables, but they do have exactly the same distribution. It happens to be binomial, with parameters 10 and p equals 0.5. Moment-generating functions uniquely determine distributions, not random variables themselves. The second result, which is important in application, is a convergence theorem. It says that if we have a sequence of moment-generating functions, we have random variables xn with moment-generating functions mn of t, and let's suppose for each value of t, mn of t converges to some m of t, I've called it. We're going to assume that we know m of t is a moment-generating function of some random variable x. If that's the case, then xn converges in distribution to x. And remember, that means that the cumulative distribution functions of xn converge to the cumulative distribution function of x. This will become a little clearer with an example which confirms something we already know, namely that under some circumstances, a binomial distribution is very close to a Poisson. So let's proceed to that example. Suppose my random variables xn have a binomial distribution with parameters n and p. The first thing I need to do is find their moment-generating function, mn of t. We do that by adding up the values e to the xt times the binomial probability function n choose x, p to the x1 minus p to the n minus x. Now it's just a question of evaluating this sum. And again, I see two quantities which are raised to the power x. I might as well pool them. E to the t is raised to the power x, so is p. So we'll rewrite this as the sum n choose x e to the tp, the whole thing raised to x, times 1 minus p raised to the power n minus x. And now if you go back and check what the binomial theorem says about such a sum, that's an expansion of something that looks like this, a plus b raised to the power n. A in this case is e to the tp, b is 1 minus p. So the binomial theorem gives us an expression for this sum. It's p e to the t plus 1 minus p raised to the power n. We've found the moment generating function of a binomial. Now I want to see what happens when n is large and p is small. And to that end, let's let mu be a parameter, I'll call it n times p. We're going to hold mu fixed, let n go up, and let p go down correspondingly. I've rewritten mn of t as 1 plus p e to the t minus 1 raised to the power n. And since p is mu over n, I can make that substitution. And then I see something which resembles a quantity that appears frequently in calculus, a quantity that looks like this, 1 plus c over n raised to the power n. Again, that's a very important limit in calculus. With c equals 1, it's often used to define the transcendental number e. As n goes to infinity, 1 plus c over n to the power n converges to e to the c. And if we use that here, we discover that 1 plus mu over n times e to the t minus 1, all raised to the power n, converges to e to the mu times e to the t minus 1. You may not recognize that because it's on a previous slide, but that is, in fact, the moment generating function of a Poisson. Under these circumstances, as n goes to infinity, a binomial approaches a Poisson. The binomial moment generating function converges, and therefore the distribution converges. This confirms something that we've known for some time, that for very large values of n and small values of p, the binomial can be adequately approximated by a Poisson distribution. The binomial gets closer and closer as n grows. Review problem. Find the moment generating function of a random variable which has probability function p times 1 minus p to the x minus 1, where x runs from 1, 2, 3 through the positive integers. Use the moment generating function to find the expected value of x. Solution. M of t is the expected value of e to the xt, which we can write down as usual as the sum over x e to the xt times f of x. And when we substitute the probability function, we discover, once more, that there are two terms, both raised to the power x minus 1, e to the t and 1 minus p. And it's always a good idea to pool those two terms. If I do, I'm left with two quantities outside the summation sign, namely p and e to the t. Inside the summation sign, I have a usual geometric sum, the sum of a geometric series. And so when we replace that by its sum, we're left with p e to the t 1 minus e to the t 1 minus p. We've discovered the moment generating function. If we differentiate it, this is standard algebra, and substitute t equals 0, we end up, after some simplification, with 1 over p. That's the expected value of this random variable, 1 over p. Review problem 2. Suppose I have two random variables, x and y. X has moment generating function m1 of t, and y has moment generating function m2 of t. Suppose x and y are independent of one another. I'm interested in the moment generating function of their sum, x plus y. In this case, I've given you specifically what the two moment generating functions are, but the more general observation is that I can find the moment generating function of the sum of independent quantities using their individual moment generating functions. In general, finding the distribution of the sum of two random variables is quite hard, but finding the moment generating function of that sum is quite easy. So moment generating functions convert a difficult problem to an easy one. Solution. The moment generating function of x plus y is the expected value of e to the x plus y times t. And we can write that quantity as e to the xt times e to the yt. Notice now that we're taking the expected value of a product. A product, indeed, of two independent quantities. E to the xt is independent of e to the yt because x and y are independent. And so the expected value of a product under these circumstances is the product of the expected values. This factors into the expected value of e to the xt times e to the yt. This tells us that the moment generating function of x plus y is the product of the two individual moment-generating functions, m1 of t times m2 of t. This is what I meant by converting a hard problem, a distribution of x plus y, into an easy one, multiplying together two moment-generating functions. When you substitute the moment-generating functions we have in this instance, p e to the t plus 1 minus p the quantity squared, and a similar quantity cubed, we end up with p e to the t plus 1 minus p the whole quantity to the power 5. According to the last slide, this is the moment-generating function of a binomial distribution, in fact, with n equals 5. What have we discovered? When we add together two binomials, x plus y, each independent, one with n equals 2 and the other with n equals 3, the result is a binomial with n equals 5. Of course, in all cases, the probability of success p was the same. The sum of independent binomial random variables with a common p is also binomial. This shouldn't be surprising. If you count how many successes you got in 2 trials, and you add the number of successes you obtained in 3 more trials conducted independently, that sum is the number of successes in 5 trials, a binomial random variable.